All right. Hello, everyone. Okay. Hello, everyone. My name is Magali Billen. I'm a professor up at UC Davis, and I am a geodynamicist. I've spent most of my time focusing on various different aspects of subduction, going from the very shallow processes, faulting and fracture at the trench, down into deformation within the transition zone. I haven't actually done any work on what happens to slabs in the deep mantle. Okay, so what I'm going to be doing today is sort of setting up what you might think of as the initial conditions or the boundary conditions for what happens to the slab as it goes into the deep mantle. And so I'm going to start very broad and very shallow and be trying to work my way down and give you some idea of the kinds of things that are happening in the upper mantle, which will have a profound effect on what the slab actually looks like when it goes into the lower mantle and how it gets down there. Okay? Please interrupt to ask me questions whenever you'd like. I get really worried if nobody talks back to me. I feel like somehow I've stopped speaking or something. There's no sound coming out of my mouth. Okay, so ask me questions. Okay, so let's just start out with a simple overview of subduction. And subduction is complicated, so making it simple is starting with the basic geometry, I think. So this is a 3D cartoon drawing of the subduction zone. And the first thing is to consider is that the plate that ultimately makes it to the subduction zone is formed at an oceanic spreading center and then has to move across the ocean basin where it thickens and cools and thickens, growing a thick, strong lithosphere in that process. It has a buoyant oceanic crust. And also a buoyant Hartsbrigadic layer, which is the layer that has been melt depleted in order to form that the crust. And that layer can be very important in terms of the behavior of a plate or a slab because it's also very dry. And we know that dry rocks are usually much stronger than wet rocks. Once the plate makes it across to the subduction zone, we know from our intro geology class that eventually it gets dense enough and it becomes unstable. We don't really know exactly how that happens. And will subduct underneath an overriding plate and eventually come into some shape that looks like this. At the trench, there's usually a little bulge that comes up that is a sort of a flexural bulge of this plate that's called the outer rise. And at that point, you start to get significant faulting of the crust and possibly going into the mantle part of the lithosphere. Okay. That faulting is significant because it tends to draw water into the slab, and that water can be important for the strength of the slab, as well as what happens here in the mantle wedge, the dehydration and melting going into the arc, but also in terms of seismicity in the slab. Dehydration can embrittle or strengthen the slab at depth, and that can be a trigger for seismicity. Okay. And so eventually this is going to go down into the mantle, and what this looks like, its shape, how it deforms, is going to depend on the forces that are acting on that plate. So what we want to do is we want to figure out what observations can we make of subduction zones in order to understand the physical processes that control this the physical sort of behavior that controls this process on Earth, okay? Subduction on Earth is very particular, right? And we know from lots of numerical simulations that we can make things that have plates and move around with sort of what that looks like mantle convection, but there's some key things that look like our subduction that don't just magically appear in every numerical model we make. So the observations are telling us about what is the key characteristics of the rheology, of the heat flow, of the energy, and how that energy is dissipated in the system that actually defines how subduction looks on our planet. Okay? So what I'm going to do, we're asking this question, which is basically the big inverse question, right, that we're all trying to answer, which is how can we use these observations to learn about the processes that are active in the upper and lower mantle without being able to go there directly? So here's an outline for what I'm going to try to cover. I'll say try because I hope you interrupt me and maybe I don't make it through the whole thing. And so first I'm going to start out with what are the key observations that constrain the dynamics of subduction. These are mainly shallow upper mantle constraints, okay, at this point. how do end-member models inform our understanding of subduction? I'm going to introduce two end-member models that we know both of them are wrong, okay? But they're very, very useful for building your physical intuition about what is important at different stages of subduction. Is it the strength of the slab? Is it the viscosity of the mantle? Is it the density of the slab? What's actually controlling the deformation at different stages, okay? And then I'll explain a couple of simple approximations, mainly for temperature, but I'll also do a sinking calculation for like how long it takes the slab to get to the bottom of the mantle. And then finally, I'm going to walk through what are key processes during different stages of subduction. Okay? Any questions? Okay. All right. So first, I have a repeated slide. That's funny. Okay. First, let's start out with what I think is a fundamental observation about subduction on our planet. Subduction on Earth is one-sided. Okay? Now this may seem obvious because we've known it since, this is what we see. This is what we're taught in our intro geology class. But I'll note that subduction was the last process of plate tectonics that was understood. It was only understood really after the 1964 Alaska earthquake, in which it was demonstrated from the deformation above the subduction zone that you had to have a megathrust going down hundreds of kilometers, okay? And that was when it was understood that you have basically a subducting plate that goes from basically flat lying, right, and slowly curves into the mantle, and that the overriding plate is not participating in that sinking process. Somehow it gets mechanically decoupled from that subducting plate and remains on top, okay? And we see this in this is Honshu, this is Tonga, this is a nice 3D image of the Gorda plate from Richard Allen's website with the Yellowstone hotspot sitting right there. So on our planet, subduction is one-sided, okay? We know when the models that I do, when we do subduction modeling, we basically start the system in such a way that it can only have one-sided subduction. But there are people who work on the larger scale dynamics of trying to create plate tectonics from first principles. And for a long time, all of their subduction zones looked like this, okay, where you have a plate coming in this side, so that the color scale is reversed, so red is cold and blue is hot here. So they would have a plate coming in and a plate coming in, and it would sink, but it would sink like this, okay? That's not what we see on our planet. Okay, and for a long time this was confusing. People thought, is this rheology? Is this something about water? Is it something, what actually creates that asymmetry? All right, and it turned out just a few years ago that there was some insight from some 2D models of subduction that showed that basically the boundary condition on the top of these numerical models, which is what we call free slip boundary condition. The free slip boundary condition basically means that you have a wall. Okay, and you can't flow up against it, right? The velocities coming up go to zero, and so the flow has to be tangential to that surface. Okay, now the Earth does not have a free slip boundary condition on the top. It has a free surface. The surface of the Earth can move up and down, and even though the topography that we see, right, maximum of 20 kilometers or so, is tiny compared to the radius of the Earth, that the stresses involved in holding up that topography are significant enough that they can actually create basically the natural conditions, all right, to create an instability so that one side of the subduction will win. Okay, so in this model, what they've done is they've taken off that free slip condition, allowed that little bit of flexure of the plate going into the subduction zone, and now in these global models, you can actually develop one-sided subduction. Now that's important when you're trying to look at the long-term evolution of subduction, because this slab looks very different than that slab. This one is thinner. It ends up actually rolling back. Okay, this one is very thick, and it tends to, but they almost always sink vertically with some mantle flow that ends up actually moving them around. Yeah.
I don't believe that at all.
You don't believe it at all. Okay. What was your thought? Because I thought this is pretty significant.
It's a complicated story,
okay,
but I would like to know that there are some, including myself, who think that the free surface is not at all required for one-sided subduction. And the weak crustal layer, sort of by default, does that for you. This particular model setup is very complicated. I had a student trying to reproduce this and trying to simplify it for years, and I've talked with the authors and co-authors of that paper.
Okay.
What is perhaps important to take away is that those modifications make the system very transient and lead to very strong rollback, which is naturally one-sided.
Okay, all right.
And this would perhaps not be a mechanism that could sustain plate tectonics because the surface boundary layer is just quickly consumed.
And having the free surface? Or having...
Well, due to their particular setup, it's very time dependent. So they don't really get long-term plate motions. And also, there are ways to approximate the behavior of the free surface with a free slip surface that do just as well.
By putting in a weak layer underneath it, like a crust, or?
By putting in plasticity.
By putting plasticity.
What is important to note is that the stresses are indeed different, right? And you are treating different mechanics.
You have to treat, so I guess the take home from this is that you have to treat the mechanics of the boundary, the top boundary, such that flexure, the plate can actually deform as it wants to. Okay, so maybe they were too extreme, so they ended up getting very transient behavior. Okay, I would
just like to note that there's not consensus that those are the two required ingredients to have one-sided subduction.
Okay, perfect, that's fine, yep.
But it's probably a combination, right, in reality?
Yeah. Yes, you need to have a good rheology, a realistic rheology of the plate, so that the top can deform differently than the bottom. But I think a free surface is important, because even if we do a free slip surface and try to produce like realistic depths of trenches, right? It's very hard to do that by just putting in plastic crust.
Yes, it depends on what you want to do.
Yes.
But
good.
but what makes it hard is that if you put in a kludge, a fudge factor, then you cannot attribute this fudge factor, say plasticity, to actual plasticity in rocks.
Right. Okay.
And so if you have a free surface, that makes it easier to
figure
ask
out
that question.
What is actually controlling it.
No doubt.
Yeah, we're totally agreed. All right. Yes, Laurent, more. See, this is great. I won't get through anything.
I'm going to address the second point. Do we need a weak crustal layer or just some weak layer or decoupling layer? Does it have to be crust?
Well, if the sticky layer ends up making it too transient, probably because the low viscosity sticky layer gets entrained into the subduction zone, is my guess, then something more, by putting in something that we know exists, a crustal layer with a different rheology would be a better choice, right?
So I am thinking of, faults and fault mechanics about the interface at depth, whether they could actually weaken by themselves, maybe because of hydrations or something that may happen at the fault surface, not necessarily in the finite thickness crust. Is what I'm trying to ask.
Okay. We don't know because we haven't done those models yet. Okay. So all of those things are great. The key point, which actually this whole discussion points out, is always ask what the boundary conditions are. They have a huge effect. And we clearly are still debating amongst ourselves what the best boundary conditions are, but they affect what you see in these models. Okay? And so you have to take them into account. I actually will not show very many
I want to ask a naive question. So the weak, can you define the word weak? Do you mean it's brittle? Or what is weak, what is strong?
Okay, so it depends on what part of the plate you're looking at. So if you're talking about the brittle part of the plate, it would be a low coefficient of friction or transition to plasticity as you go down in depth at higher pressure. It could also mean, in the viscous part of the mantle, a low viscosity. Okay, so it depends on what part of the system you're talking about. Okay, so the next key observation, which is important, is the topography. And so I just walked through what the topography is first. So here we have, this is a profile across the Mariana Trench and Island Arc. And so here you have the Pacific Ocean coming in. And this is, by the way, hugely vertically exaggerated. Okay, so this is minus 8,000, minus 4,000, 0. Okay, so this is depth into the ocean. So this is the Pacific plate coming in. Here you can see this bulge of the outer rise, which is very typical in most subduction zones will have this. It varies in height, it varies in width and curvature. Then you have the trench, okay, which is this the deepest feature going down to more than 10,000 meters in some part of the Marianas Trench. And then there's this forearc high, which is not totally understood. And then you have the arc. And then you have the overriding plate, which in some places has a back arc basin, which I can't remember whether it's here or here. Okay? So what the topography is telling you is basically about the stresses on the plate within the subduction region. And these are very small amplitudes in compared to the size of the rest of the subduction system, but they're important for all these things we just discussed in terms of what is the rheology of the plate that's deforming, how does it actually go through that deformation. And then on the overriding plate, you actually see that you have generally higher topography, right, than the old Pacific plate on this side. This is actually is somewhat surprising if you actually think about the flow underneath. This plate goes down underneath here and is sinking, okay? And so it actually wants to pull the overriding plate down with it. And yet we don't actually see that in the topography. What we see is generally high topography. And so this is also telling us that you have some decoupling between the flow and what's happening at the surface, which is telling you about rheology or other complications in the subduction system. I also showed here, this is actually a picture from Google Maps. So if you go into Google Maps and put on the terrain topography view and you go into the oceans, you can see all of the swath bathymetry data that has been collected by the United States and other places that's been pooled together. And they've embedded this into a smooth image of topography based on gravity. So if you just zoom in, you'll do this when you get bored of the talk. You zoom into these areas, you can see all of the topography off the coast because most coasts have been mapped very well. But then you can follow these ship tracks across all the ocean basins and see the ridges that they've mapped and the subduction zones, seamounts, all of those things. Okay? So it's really crazy. This is actually data that I collected, and it's in Google Maps. Yay! Okay. Okay. So the next observation as we go down is seismicity. And seismicity is important because it tells us about the shape of the slab, but it also is limited because we only have seismicity in the upper mantle. Right? The seismicity stops abruptly at about 660 kilometers. It has an activity minimum around 350 kilometers, and this activity varies a lot between slabs. So to illustrate this, this is a view looking down into the earth, looking east. Whoa. Sorry, that was interesting. It wants me to log into EduRoam. Okay. This is a view looking down to the east. You have the Kuril subduction zone here. The Pacific plate is back here in black. This is the Isobonine, and this section right here is Japan. This little arm right here is the shallow seismicity from the Nankai Trough. All right? And so what you can see is that this is starting at 100 kilometers, so we cut everything off at the above in the overriding plate, so you're just looking at seismicity in the subducting plate. And you can see that there's lots of seismicity near the top. All of these little green dots are earthquakes down to magnitude 4. And then there's this gap, okay, and you see it over here too. And then you have an increase in the seismicity as you go deeper down to 660 kilometers. And these pink and blue ones are all big ones, like magnitude 7s and 8s. Okay? So this picture is just a snapshot I took of a particular area, but all the subduction zones generally have this sort of behavior. Some of them have much less seismicity, so it's harder to see this pattern, but in places where there's significant seismicity, you can see this pattern. And so the seismicity is reflecting how the slab, what its shape is, right? This is how we primarily know the shape of the slab in the upper mantle. But it also, we can use the moment tensors from these larger earthquakes to figure out what the stress state is. Okay? And so for those, not everybody's probably familiar with moment tensors, but a moment tensor is basically a way of using the observed seismic waves to invert for what would have been the strain at the location of the earthquake that caused that deformation. People often say stress, but we actually don't know the level of stress, so it's actually more the strain. Okay? So you can get a principal compression axis and a principal tension axis and a neutral axis. That brings in a bunch of assumptions, but it's a good way of getting a sense of what is the average stress state at the location of the earthquake. And so what this figure summarizes is for a bunch of different slabs, what their general shape is thought to be from the seismicity, in some places extrapolated where it's not where there's no seismicity. And then these dots are colored blue for where there's generally down dip compression parallel to the dip of the slab, and red where there's generally down dip tension, I believe. Yes, I think that's right. And then in between there's some axes that are not exactly down dip tension or down dip compression. Okay, and so there's an overall pattern. Some places like Tonga are completely in down dip compression, okay, whereas other places like Chile are in tension at shallow depths but compression deeper down. Okay, and so these moment tensors, these stress axes, are one way that we can get at how is the slab actually deforming? Is it stretching? Is it under compression? Is it buckling and folding? Because when we just look at the seismicity, right, what we tend to think is, oh, the slab is subducting parallel to that shape, right? That's the flow is parallel to the shape. That is not true, okay? This material here did not necessarily go down here, go backwards, and then fold under, right? That is not the path that the material took. The material might have actually gone like this, okay? But then the slab buckled, all right? So don't look at the shape of the slab and think that that is the track, the path that material took to get into the mantle. Okay, that is not necessarily true, and actually most places it's probably never true. Okay, because we don't have infinitely stiff slabs; they deform and they sink. Okay, so to give you an example of what we can learn, I'm going to zoom in on just two sections. This is from this part of the Japan slab. First, I'm going to show a cross-section across this, and then I'm going to show a face-on view of this area between Japan and Izubonin. So here's a cross-section of the Japan slab, and these axes are the compression axes, and you can see that these are just amazingly aligned in this really thin zone, down-dip compression. Okay, it's a beautiful, beautiful zone. But when we look in this, there's a couple of outliers. You know, is that a location mistake, or are there actually earthquakes happening in this part of the slab? If so, what is that telling us? I have no idea. Okay, I'm just beginning to look at these and very interested by sort of what actually controls a very thin, narrow layer versus a thick layer. These could be phase transitions, it could be temperature, there's all sorts of things. Right? This is down at 660 kilometers, this bottom depth here. So this is what we in some places you see this very, very uniform pattern of stress. And in other areas, you have small regions that deviate from that overall simple down dip compression or tension. And so right here, this is the Japan slab, and this is looking face on to the east. And so this is down here at about 450 kilometers. This is at about 250 kilometers. The Japan slab is in down dip compression, all right? And so is the Izubonin slab right here. But there's this 100-kilometer wide section in which the axes are all the principal compression axis is rotated perpendicular. This section actually has tension axes in this orientation, which I just don't have in this picture. Okay? So what that actually shows is that the Japan slab is really deep. It's going down this way. And the Kuriles is actually steepening in this direction. And this is the point where the plates are actually diverging away from each other. Okay? So the moment tensors, there's a lot more information in here when you start looking at the details, which can help to understand how much are the slabs deforming, which is important for how weak they are and how they deform, right? What's the rheology? That's important. Okay, so going, yeah?
Those moment tensors reflect deformation presumably in the upper part of the slab.
In the coldest part of the slab, which is not necessarily the upper part of the slab at this depth.
The question is, so we're imaging the middle part of the slab. Is there a reason to think the top or the bottom have a different strain?
They could, yeah, but it may be that they're also too warm to be supporting a lot of stress, right? So that you have the coldest internal part of the slab is probably where most of the strength of the slab is being held. The other outer parts, as you get much warmer, are going to start to flow and deform viscously. They're not actually going to support the slab. But Torsten, please.
Well, I think to some extent we see the expected bending.
At shallow depths.
It's at shallow
depths.
And
yes.
I think the Alpert figure had some places where we felt it was significant enough to have a difference in the top and the bottom.
Yeah.
But it's kind of hard to get the systematics out.
Yeah, so in places where you have double Benioff zones, right, sometimes the separation, I think, is enough. Brad, do you have a comment?
Yeah, how do we know that the deformation is in the coldest part of the slab? I mean, at shallower levels, it's clearly not.
Can you repeat the question?
Okay.
Yeah, how do we know that the deformation is in the coldest part of the slab at depth? At shallower levels, it's clearly...
Okay, so it has to be in the colder section in the center, because the warmer sections outside are not going to be able to hold stress, right, because they're going to be flowing. So there's going to be a temperature cutoff, probably somewhere around 800 degrees, maybe cooler, depending on what sort of plasticity is actually occurring, low temperature plasticity is occurring in the slab. So we actually don't know that answer, but it has to be the colder part. So I'm going to show some temperature profiles later that I can refer back to that question. Okay? Yeah, Jonathan?
Do these breaks like this one here correspond at the surface to places where, for example, it transitions from being curved to straight, like where there's sort of corners?
So
in the subduction zone?
In this place, actually, so if I could show you a movie or take you into the cave, our 3D virtual environment where we map all of these things, what you would see is that there's actually a curvature to the slab like this at the location of these slabs. And that is where the cusp in the trench is at the surface. So we're looking at a bunch of things like this. There's also like clusters of seismicity that come down in stripes, and people have seen some of these patterns. They may be related to fracture zones that are being subducted that maybe are more hydrated or have different minerals in them. So there's a lot of complexity in here, and there's been different studies on different parts of it. Yeah. So I can't go into all of that, but there's a lot of information in the moment tensors. Yeah.
So that's exactly my question. I have a hard time understanding that diagram. We don't physicists.
I can try to explain.
But what are those green dots? What are those?
Okay.
What is that cross in the center?
Okay.
Are we looking down or looking
Okay,
up
I tried to explain. Okay, let me go back. I'll go back.
And what are those blues and dark,
Okay.
dots in the behind?
Okay.
Yeah.
All right, so let me start back with this picture, okay? So you're in a ship above basically China, all right, northern part of China. You're looking out to the Pacific Ocean, up, and you have the Japan islands would basically be sitting on top of this, right here, okay? And now what you're seeing is the seismicity diving down into the Earth, okay? And all of the dots, green, blue, purple, are all earthquakes. The green ones are magnitude 5s. As you go to blue and purple, those are larger magnitude earthquakes. So this is the seismicity that's actually showing you the shape of the slab. So the Kuriles is basically shaped like this. The Japan next to it is a very flat, long slab that dips out, it barely shoots out. And then the Isobonine is going off in that direction and is actually very steeply dipping, okay? So this cross-section here is a cross-section across here looking this direction, but down in the Earth, so that you can actually see that seismicity down at 600 kilometers, okay? The colors in this picture is that there's a transparent Earth map on top of this that helps you locate yourself, okay? In this picture, there's a scale bar right here. This is 100 kilometers. This was to help us locate exactly where this feature was within the slab. So I took a measurement in our cave of the actual latitude, longitude, and depth, so I could come back to this location, right, and know exactly where this picture is.
And
a cave is a 3D virtual environment that you can stand in. It has 3 walls with projectors behind it as a projector that points down on the ground. We can take our data in there and we put these tracking glasses on, and the data basically pops off of the screens into a 3D actual virtual Earth structure. I can show a video of this later during some other part. And we can then actually go into the cave and stand inside our data and actually explore all of this data in the 3D environment, which it turns out is really, really helpful in looking at the 3D shape and structure, because you actually have the full shape of the slab around you. You don't have to rely on cross sections or map views. Barbara, did that answer your question?
I still don't understand that lag in
The black and blue is just a map that's on the surface. You don't have to just ignore the black and the blue. It's just a map. This isn't a globe. I can show you this during a coffee break. Okay.
Just briefly, also for comprehension.
Yep.
So Japan is under compression like this.
Yeah.
And now I need to use the other hand. And what you're showing is that there's another slab that's sort of bent over. And we're looking at this cusp region where it's stretching.
It's stretching.
Okay.
Yes, it's bent over like this, and it's stretching apart like that. Okay.
Are you going to show some tomographic images? Because I think, the recent... Oh, yeah.
I was trying. Okay. I have some movies of the Japan data that I can show people to try to explain that better, but I really didn't expect that I was going to spend that much time on it, but that's great. Now we all know more about moment tensors and that there's a cave. Okay, so the seismic tomography, is the next key observation in terms of the shape of slabs. Okay, this is how we can get to the deeper part of the mantle and what the shape of the slabs are beyond the seismicity. And in a lot of areas, the seismicity is very sparse, and so the tomography is key for actually filling in between those seismicity gaps. Okay, I don't want to. There will be lots of seismologists talking and arguing about the tomographic features. I don't want to argue. I picked one off of a paper that I had that I wanted to illustrate the variation. Okay, I'm very agnostic about which models. I'm learning about them, right, in terms of which ones are the best to use. Okay, the thing about profiles is that they don't give you context of the whole 3D shape. Okay, and so just keep that in mind. So here is a profile for the isobonin. Okay, we were actually looking at, here's Japan, here's the Kurils going in this direction, and here's the isobonin. Okay, so these 5 profiles are for isobonin. All right, and you see this is the seismicity, or the little dots inside here. They go across the 410 and the 660, and then this is 1,000 kilometers. And so this is what you see from the seismicity are just those dots. Okay, and now the blue areas are areas that are fast, and so therefore presumably colder. Right, and this is where you see how the slab actually extends into the transition zone, that area between 410 and 660 kilometers. Okay, and in this area, it appears that the slab actually flattens out inside the transition zone for quite a ways, right, going off. All right, whereas as you go further south, right, this is the northern part of the Marianas. Okay, here you have so you go from this one to this one, or it starts to get very steep, okay? But here you see that there's actually this anomaly that's going down to about 1,000 kilometers, right? And it pretty much just goes vertically straight down, all right? So the seismic tomography shows I have another set of profiles that are more controversial for the Middle America, right? So here again you see a slab that goes through the 410. It has some sort of dip, maybe between 660 and 1,000 kilometers. This slab is not currently in the transition zone. Maybe it was held up in the transition zone in the past. I don't know. But it definitely seems to be flattening out right now. But then you see there's some blobs in the lower mantle which may or may not be connected. Okay? As you go further north, you get to these sort of canonical profiles that people debate a lot, that show a slab that seems to go all the way down to the core mantle boundary. Okay? So we can argue, the seismologists will argue about what these images show, and we should let them argue and ask lots of questions. But my point is that these are the observations we have that we have to figure out. Okay? The tomographic images are the only thing that basically connect everything that we can figure out in the upper mantle to the lower mantle system. All right, and I'll come back to that later. So here's it's all complicated tomographic images. So all of these profiles show very different structures.
Sorry,
yeah?
Can I interrupt 1 second?
Yeah, sure.
Can you go back to the tomography picture, the previous one to that? Something I want to point out here is what you see, the blue there, is about 20 million years of subduction, given the rate of descent.
Yes, we're going to get to, maybe we'll get to that.
That disappears, and you just don't see any slab anymore. And I think this is a general point in our interpretation of these pictures in tomography and subduction. Subduction isn't constant forever, so that, it should go to the core or whatever, pile up in the transition.
Well,
it moves around, it starts,
yes.
it stops.
Not right,
in this location,
but in lots of locations. Yes.
So.
Yeah. So I'll come back to this with the stages of subduction so that you actually get slab break off. The slab can break in various different locations so that and subduction can start and restop. It moves around. And so actually connecting what you see in the deepest mantle to what you see in the surface is not as easy as tracking the blue dots. And for the same reason that I said the flow doesn't follow the seismicity, right? That's not the path the material took. You can't interpret it that way. Yeah. Yeah, very good point. Okay, so what questions that the tomographic images bring all sorts of questions in terms of why do these look different, right? Why do different places look different? So some things to think about. Are these at different stages of interaction with the transition zone and the lower mantle? Okay, I can give some examples of that later. It could be buckling and folding. It could be stagnation. It could be slowly sinking vertically and then getting entrained with different flow. Are there differences in slab properties, old plates versus young plates? Okay, presence of an oceanic plateau. There's all sorts of things that come into making the picture more complicated. Are there differences in the surrounding mantle properties? Okay, composition turns out to be really important for rheology. Right? And so if you have places that have had extensive depletion through melting, that may have a very different rheology or behavior than an area that's more fertile. And then finally, differences in surrounding mantle flow. A lot of subduction models have been done in an empty box. Okay, slabs just sinking into a box that only responds to the slab sinking. But in the real Earth, slabs are sinking down, plumes are coming up, you have large-scale mantle flow, and so a lot of what we see in the shape of slabs may depend on what the larger scale flow is around it. Okay. All right. So now I wanted to talk about two end-member models. To help us thinking about building that physical intuition for how slabs deform. And these are somewhat, the rigid slab corner flow is sort of a very canonical end member. I chose another end member, which I call weak slabs, which is basically just the other extreme in terms of strength. And it's based on a Stokes sinker. So I'm going to go through for both of these, what is the model, why is it useful, but what are the assumptions and simplifications that you have to keep in mind. And the key point here that we'll get at is that the slab behavior is determined by a balance of the driving forces, which are basically the buoyancy forces, compared to the resisting forces, which comes down to viscosity of the slab itself and of the surrounding mantle. Okay. So first, this is a picture that basically summarizes all of the forces that go into a subduction system, and some of them there's other ones that we could add on here. But you have ridge push, which is from the height of the ridge, the buoyancy at the ridge. You have all of the basically density anomalies within the slab itself. First, the blue here is showing the thermal buoyancy just due to the cold slab being more dense. But there's lots of other anomalous densities in here which comes from phase transitions. At the 410, you could have a positive force pulling down. Okay, positive forces are down in this picture from a elevated olivine to Wadsleyite transition. It's elevated because it's colder in the slab, and so you go to the denser phase at a shallower elevation than the surrounding mantle. Similarly, at the 660, the cold slab, the transition from spinel to perovskite happens deeper, and so this area is actually more buoyant than the surrounding mantle at the same temperature. Okay. Alternatively, if you don't just easily transition from olivine to Wadsleyite, you can have a metastable phase within the slab, and that means that I actually have the buoyant phase being dragged down into the transition zone, so this green tongue is basically less dense than the surrounding area, and so it has a negative buoyancy, negative density difference. Okay, so it's actually going to resist subduction. All right. So there are lots of other phase changes in here. You could also consider that the crust and the Hartsbrugite layers have transitions at different depths. Okay, they're going to go through transitions, some transitions that other layers don't. So you have all of these density variations. That's basically what's the main driving force for subduction. Okay, but you also have the larger scale mantle flow. So the upper mantle, the flow could actually be from a large plume coming in and actually driving flow in the direction of subduction, or it could actually be opposing subduction. Okay, and then finally, we're going to talk about this suction force here in more detail when I talk about the corner flow. And this is a force that is basically caused by the flow, which actually helps to sort of pull up the slab at shallow depths. And then the last thing here, as you go into the deeper mantle, you have an increase in viscosity down here. You're going to have more resistance, viscous resistance to flow as you are sinking into a higher viscosity mantle. All right. So before I go on, there's a bonus question. There's an error in this figure. We'll come back to it. Do you know where the error is?
No. I just want to ask you, when the slab subducts, what is the erosion of the thickness of the slab? Is it uniform, or is the thickness of the slab is also eroded?
Start the beginning of the question again.
When
sorry.
the slab is subducting, let's say the oceanic lithosphere is 70 or 80 kilometers.
Right, for a cold old slab.
During the subduction, what is the thickness of the slab? How is eroded? How is it disturbed by the subduction? Okay, so
I'm going to show some thermal profiles later of that. But in general, what you're going to inherit the thermal structure of the slab from the cooling of the lithosphere as it goes in. Okay, the difference is you're going to basically, the top of the slab is coming in at 0 temperature, right? And as soon as it hits the mantle, it's going to heat up very quickly, and that means you're heating up the slab, but you're actually cooling off the mantle around it. So thermally, the slab is going to expand somewhat, okay? But the mechanical thickness of the slab, which is mainly determined by its temperature, right? You have strongly temperature-dependent viscosity. The mechanical thickness is slowly going to decrease because the cold region is getting smaller over time, okay? But in the upper mantle, that diffusive thickening is not very much because slabs sink pretty quickly through the upper mantle. Yeah?
I think if the slab is depleted, like you said before, it's very dry, I think it will remain the thickness for that dry part.
For a very long, yes, because so the Harsbergite layer, which is maybe about 15 to 20 kilometers thick.
Right, it not depends on temperature. It depends on more like on condensation, right?
Well, no. I mean, it depends on what viscosity law you're using, right? So water content, as you go from dry olivine to wet olivine, only gives you a factor of maybe a few thousand.
My comment is the thickness of the Harsbergite does not depend on temperature. So
no, the thickness of the Harsbergite, no. Yes. I'm just saying the thickness of the strong part, the part that is mechanically strong, which depends on the dryness, right?
Okay.
But also the temperature. And here I think it's going to be primarily dependent on temperature.
Thank you.
Okay, yeah.
A question about the term close to surface flow suction.
Yes, so I'm going to come back to that with the corner flow calculation. Okay. Yes, let me get there. Yeah. Okay, so there's an error in here, and I'll give you a hint. It's one of the arrows. Okay. What?
There's more than one.
There's a lot of arrows. Yeah, we'll come back to it. I'll tell you where it is later. But it was published, so it was like, damn it. Okay, so this is actually a very schematic view of the rheology of this. Okay, and there's a lot of information in here, and I was originally supposed to give my talk in the second week after all of the rheology was talked about, and so we have to just. I don't want to go into this super detailed. Okay, the rheology, the strength here is going to depend on composition, as we just said, basaltic versus Harsbergitic. It's going to be cold in this center part. This is where you're going to have the highest viscosities, 10 to the 24, 10 to 25 pascals, maybe. Okay, but you're going to have serpentinites forming. Those are weak. All right. You have faulting in here, which is hydrating this part. That's going to have a different rheology. You're going from basalt to eclogite. Eclogitic crust might be much stronger than basaltic crust. And then surrounding this, all right, this upper part of the mantle is going to be deforming by a non-linear, non-Newtonian viscosity. And so here, where you have high stresses of the slab pushing down through that mantle, the stress dependence is going to create a very weak layer within the mantle wedge and on the boundaries of the slab. So even though you're increasing the thermal halo of the slab, right, the shear is actually going to decrease the mechanical thickness of the slab. All right. And then surrounding that, I just drew kind of the basic layered structure that we imagine exists based on the experiments. Okay. All right. So these are the kind of the simplest but complicated pictures of the rheology. So now let's step back and just think about what's the main physics going on in subduction. Okay. So I call this the weak slab model, but it's basically getting at what would happen if subduction was just controlled by density. Okay, if the strength and all of this rheology and stuff was not actually that important. And some of the earlier models of subduction and plate motions were basically run by just having dense blobs falling into the mantle at the location of slabs. And they actually did a not bad job of describing what plate motions are. Okay, so the first order, you can think of the strength is actually not that important, right? You can actually do a lot without considering all of the rheology. All right. So the way that the important thing to think about in terms of sinking, okay, of just the buoyancy of the slab, is you can use a sinking sphere model. Okay. So here's a sinking sphere in a viscous material. The flow is going up around it relative to the location of the sphere. You have the gravitational force from the density difference between the sphere and the surroundings, and then you have the drag force from the viscous flow around that sphere. And that's the same thing we have in a subduction zone, right? You have the density of the slab, and the slab is having to resist the viscous flow around it, okay? And so you can balance, I'm not going to go into details here, but you can balance the drag force, which depends on the viscosity, how fast it's sinking, and the radius, against the gravitational force, which you have the volume of a sphere, and then the density difference, okay, in gravity. And if you set these two equal and solve for the velocity, you'll find that the rate of sinking just depends on the density difference, right? That's going to increase velocity, as well as how big it is. Okay, the bigger it is, the faster it's going to sink, but it's going to be resisted by the viscosity of the fluid. Okay, and I'll come back and use this later to just get an estimate of the sinking rates, but you can see that, for example, if the upper mantle viscosity is 10 to the 20, all right, and the lower mantle viscosity is 10 to the 22, you're going to have a factor of 100 slower sinking rate in the lower mantle relative to the upper mantle. Okay, factor of 100, right there, without anything else going on, right? So if slabs are sinking at 10 centimeters per year in the upper mantle, or 5 centimeters per year, right, they're sinking at less than a centimeter per year in the lower mantle. That is really slow, all right? And we have a hard time separating that when we look at these pictures of tomography, that what's going on in the center is in the bottom, it takes a long time, okay? Okay, so here's just an example of what you see if you have a relatively weak slab in a numerical calculation. So what this model is there's a ridge right here and an overriding plate, and you can actually have flow going through this box. And there's a very small viscosity contrast. In the top, it's actually the same viscosity as the surrounding mantle. And then in this picture, it's a factor of 30 stronger than the surrounding mantle. So it's really small. And what you can see, they initiated a subduction zone here and a little initial slab. And so then this thing started sinking dynamically into the mantle. And this is the 660 here, and there's no viscosity contrast in this mantle. Is that right? Oh, I'm sorry. Then this one, sorry. Actually, both of these, I wrote down something wrong here. Oh, this actually should be viscosity of the upper versus lower mantle. There's no viscosity jump from the upper to lower mantle here. Here, the viscosity jump is 30. And the viscosity between the slab and the mantle is either 10 or 100. Okay, sorry. So if you have no viscosity jump going into the lower mantle, this thing basically just sinks almost vertically, right? There's a little bit of a dip, all right? And with no viscosity contrast, you basically go down, and here it's hitting the bottom of the box, so you can ignore that. Here, you have a small jump in viscosity, and this weak slab still basically sinks down, but the interaction with the viscosity jump into lower mantle actually forces it to roll backwards. So it actually rolls backwards and creates this shallow dip. All right. Here you have down dip tension in the top, a down dip tension throughout because there's no viscosity contrast. Where here you have down dip tension at shallow depths and down dip compression where it's meeting this jump in viscosity. Okay, and this isotherm here is like 0.9, so that's like a really like large thermal halo, but of a very tiny amount. Okay, it's like 100 degrees. All right, and so what is important for this type of model is that if you have a perfectly weak slab, it predicts that the slab will sink vertically into the mantle. Okay, it switches the orientation of compression from down dip tension to down dip compression if you have a jump in viscosity. So you don't need a strong slab to get this compressional viscosity, right? Compressional stress in the slab. But you do need trench motion to get non-vertical dips, okay? Because the slab is not, basically as soon as you put a bit in, it just wants to sink straight down, okay? The main assumptions or simplifications of this model is that the strength is less than expected from experiments of olivine rheology. And so we expect that the slab is a bit stronger than this, and so its behavior might be different. But this is a really good, these weak slab models are very good for getting a first order understanding of how the slab sinks through the upper mantle, how it deforms and interacts with a jump in viscosity. But as you increase the viscosity contrast between the slab and the mantle, the dynamics will change. Okay, so the other end member is to have a perfectly rigid slab. All right, and so this is basically all controlled by the fact that it's perfectly rigid. It cannot deform internally. And so before I get to what that model can give us in terms of dynamics, which seems like you might think it can't give you anything, but it can. This rigid slab model comes from a calculation of corner flow. Basically, if you have, this is from Bachelor 1967, which is an engineering application that was adapted by Dan McKenzie in 1969 to study subduction once that was understood. So the idea is you have a fixed upper plate, okay, and you have a moving lower plate which turns at a corner, okay. So you have an inside corner where there's flow here, and you have an outside corner where there's flow here. And it's being driven by these boundary conditions, these kinematic boundary conditions. You can set up the conservation of mass and momentum, which Michael introduced us all to. You can set up those equations with these boundary conditions for the flow and analytically solve for what the flow in the surrounding corners will be in response to these kinematic boundary conditions. And this is from McKenzie's 1969 paper, and these are showing the streamlines from that flow. So you have a very broad flow with pretty much uniform velocities below the plate. And then you have this very tight corner where the flow comes up into the corner, and you have a sharp gradient in velocity going from the slab to a sort of center part of the corner which is not moving very much because it has to come up and switch directions. Okay? So what can you actually predict about dynamics from this model? Okay? So Stevenson and Turner, and also another paper by Tovish and Schubert, showed in 1977, 1978 that if you look at the balance between a slab that's rigid and its density, right, and the forces that come from the viscous flow, you can predict something about what the steady state dip of slab should be. Okay, so I'll just walk you through the basics of this. So if you take this flow, okay, the fact that you have a flow at a velocity in here, if you remember from Michael's description of solving the conservation in mass and momentum, there were 4 unknowns, right? You had 3 velocities, but then you also had pressure, okay? And you can think about, in some ways, the pressure is balancing the velocities, okay, within the conservation momentum equation. So in this flow, the fact that you have a corner here, you basically, in an acute angle corner like this, you will actually have a low pressure region in the middle of this. Low pressures basically want to pull everything in, okay? That's why we call them a suction force. So if I have low pressure here, that will try to actually pull up on my slab, okay? Whereas on the outside corner, okay, we actually have a positive pressure pushing out, all right? Which means that actually I have a pressure that's pushing on the backside of my slab, pushing up on it. All right? So I have two pressures that are induced by the flow which want to lift the slab. Okay? And the big one is actually the one that's in the top corner. All right? So Mackenzie worked out these equations. So you have the pressure here, which depends on, these are the only things that matter, depends on the viscosity, depends on how fast the plate is moving, and then a bunch of just angles. Where are we in this flow? Okay? And also how far down are we along the slab? R is the distance from this corner down out, going out in a radial coordinate system. Okay? So these are the pressures that are actually acting on this slab. So we have this large pressure in the inside corner and this smaller pressure in the outside corner. But both of them are acting to lift the slab. And so your people talk about sort of the suction in the wedge. Okay, this is what they're referring to. All right. And so you can take these pressures and you can calculate that what we call it's a hydrodynamic torque, right? You basically have a force on a lever arm and you want to lift the slab, right? And it can basically only pivot at the top corner. And then counteracting that, right, is if we actually put a finite slab attached to this rigid area, that slab has a gravitational force which wants to counteract and steepen the slab. And so there you have the density contrast, gravity, and then basically the thickness of the slab, how long the slab is, and then what its dip angle is. So what Stevenson and Turner did and what Tovish did is they basically said, let's set these two torques equal to each other, and that should predict the steady state dip, right, of slabs. Okay? And at the time they did this graphically in this Nature paper. This is torque, normalized torque, versus angle of the slab, going from small angles to large angles. This curve here is the prediction for the hydrodynamic torque for a given velocity and a given viscosity. And then each of these curves are different predictions of the gravity based on a certain critical buoyancy for the slab, so varying the density difference or the thickness of the slab. And what they found is that there is a solution basically where the two things are equal, and one solution is stable here, whereas a solution over here and this solution over here are unstable. Okay? So the stable solution predicts an average slab dip of about 63 degrees. Okay? Now, this has a lot of approximations, right? Slabs do not deform like this in the Mantle. They're not paddle wheels. Okay? But this gives you a sense of like, especially when a slab first initiates, right? You have this strong thing dipping down into the mantle, and the slab is trying to basically, it's got to figure out what its dip is going to be. Initially, that dip is going to be controlled basically by this corner flow. All right, what that average dip is. And at that point, it's actually going to be a shorter slab, and so you'll be able to have actually shorter dips, smaller dips. What this also shows for the unstable sections, right, is that if your slab ends up with a smaller dip, it will be, the suction torque will hugely outpace the buoyancy, all right, and your whole slab will basically just get sucked up to the overriding plate and just shut off your wedge. Whereas if you go to very steep angles, the buoyancy forces will win and you'll just get a vertical slab. Okay? Now, these sort of three ideas, that there's a steady state dip that it kind of wants to be at if it's rigid enough, that if it's too shallow, it'll actually get sucked up into the overriding wedge, and that if it's too steep, it'll go vertical. Those are really handy things to have in your head when you're looking at a subduction model. Because when I start out subduction models, depending on what you do with it, sometimes your slab goes in and then it goes and it sticks to the overriding plate. All right? If you start out subduction and you have a craton on your overriding plate and you narrow the wedge, make it smaller, that's basically this dip angle getting smaller. Your slab will start to basically get sucked up into the overriding plate. Okay, so this model, just understanding this balance between the viscous torque and the gravitational torque, all right, can help you to understand, even though your real slabs are deformable, what might be happening in different parts of the evolution, right? Where is it that this hydrodynamic force can actually affect the deformation of your slab, Whereas where the gravitational forces are going to be really the main thing, and therefore you have to look at what's the viscosity around the system that's actually controlling deformation. Question?
Yeah, question is about, do you think the torque from the bending is important or not important?
It's important. So this is an n-member model, right? And I started this out saying neither of these models are correct. Okay. But they influence the way we think about it, right? Because the real subduction models are super complicated. They do all kinds of stuff and they do it fast. And what you're trying to break down is at different parts of the evolution of the slab, what are the processes that are actually acting on the slab? And there are parts of the subduction process at the initiation, when the slab may be being influenced by the thickness of the overriding plate, where suction in a corner is actually really important, and it plays a major role. Okay? So the real Earth probably fits somewhere in between. Okay? This is a summary drawing from a Reby paper that actually uses a thin sheet approximation. I won't go into all of that. But he showed a bunch of predicted shapes of slabs as you increase the viscosity contrast between the slab and the surrounding mantle, right? And so here is the weak slab model that basically sinks straight down, and then you increase the viscosity, and you start to see that the slab is strong enough here that it actually is basically supporting its own weight as it goes down, but then it basically gets too big, and the tip goes vertical, okay? As you go really strong, you can get these really shallow dipping slabs that basically just can hold their dip really far, and then the front will basically tip down. Okay, so the real mantle probably is somewhere, in here. It's a factor of 1,000 or so. And the thing is that what's important is that these slabs all have a uniform viscosity. The real rheology for slabs is nonlinear plastic rheology. And so some places might be really weak where other places are still strong. Okay? And so that is going to really affect the way that it deforms. So in the real Earth, right, we have a deformable slab. It's neither super weak, it's neither perfectly rigid, all right? And it has all of these forces that are acting on the system. Sometimes the suction force in the corner will be really important. Sometimes it won't matter at all, okay? Where sometimes the mantle flow will be very important. The rheology contrast will be really important. And then what actually happens as you go into the lower mantle. So everybody's looking for the mistake. So the shear forces should be both acting against the sinking slab on both sides. It's published. Well, it could, yeah. So if the mantle flow is outpacing, then it could be pushing it. Thank you. It's right. It wasn't what I meant to draw. Yeah. So if
the shear could go either way.
It could. If the mantle is going faster than the slab, then you could have shear going in the other direction. It's not wrong. Okay, good. Thank you. It's one of the end members, right? Okay. All right. So deformable slabs, okay, these ones that are strongish but deformable, okay, do interesting things, all right? First of all, they will buckle and fold, okay? And this is some examples of that, which some are kind of extreme. Don't think we have slabs piling up quite like this going into the mantle, but this illustrates with just analog materials. If you have a strong sort of viscous, flowing viscous material that has some strength, and it comes to a boundary, right? It feels that boundary basically, and it will start to fold in response to the stresses being propagated inside that liquid, okay? And if you're rolling back while you do that, you can get folds that pile up in big messes, okay? And you can get this in numerical calculations as well. This is just an example from Bahunkova and Siskova. This is their initial condition. Here's 11 million years. 22 million years, you see this buckling. Here they've had multiple buckles, and then it opens up a little bit, and the folding is not as tight. And here's what this part here, right, was up here before. And then it can keep going. And so the amplitude of folding changes in time. It can also change depending on what this rheologic contrast is in here. They have phase transitions that actually that adds to the buckling in most cases because you have an extra force here and you have this extra little resisting force here. If you do this, you include with the phase transitions the effects of latent heat and shear heating, you'll actually even weaken the slab in these areas because you heat it a little bit. That makes it easier to buckle. Okay, so these real slabs could look something like this, or not. They don't always do buckling behavior, but they can. Yeah.
I want to ask, in these calculations, is it free slip surface or you impose velocity?
I'm sorry. I can actually only hear out of one ear, so I'm going to have to come over here.
My question is for these 2D calculations, the surface boundary condition, is it free slip or imposed velocity?
This one was with imposed velocity.
Yeah,
You can get folding without it, though. I'll show you another model in which you get folding and buckling in a dynamic model without the imposed velocity.
Okay.
Yeah. I mean, in here it can seem like it's forced. They weren't moving this very fast. If you over push the slab in, you can affect the buckling behavior, right?
Yes.
But so in these models they did impose a velocity in order to see how that changed, so how the buckling behavior changed with response to the mantle structure. But I'll show you another model where we get buckling for a dynamic slab.
Okay.
Now, it's actually, I think, easier to get buckling in a dynamic slab because the slab continues to sink very rapidly in the upper mantle, and it can actually change the rate of sinking in response to the resistance to sinking in the lower mantle. So, yeah. But yes, boundary condition matters. I have other models where if you push them too fast, they just go straight into the mantle and they don't buckle at all. So that matters. Okay. Let's see. So I wanted to talk about the temperature of the slab because this came up as in many questions. I think I go till 10:30, right? I have 25 minutes. Yes. Okay. Okay, but there's been a lot of questions. Okay, but I will. I'll try. Okay, so I'm going to talk about three sort of temperature approximations that are very good to just have in your back pocket for I need to figure out what this temperature, that temperature is. So the first one is just a half-space cooling model, which I'm not going to derive. I'm just going to give you the solution. And then I'm going to show you another solution for temperature heating of a cold slab that Mackenzie first used. And then I'm going to explain why it's wrong. And then I'm going to show you some solutions for using a corner flow velocity field or a corner flow boundary condition to determine the thermal structure of slabs. All right? And I think the sinking rate I'm going to skip because we kind of touched that. And I think Thorsten is going to come back to sinking things. Okay. So the initial temperature of your slab is basically the temperature of the lithosphere coming in. Okay. And so one model for the cooling of lithospheric plates as they leave the ridge is a half-space cooling model. The reason it's called a half-space cooling model is that you basically have a region which you have a top with a fixed temperature, and then you have infinite space underneath it. Okay. And at infinity, you set the temperature to your mantle temperature, all right? So 1400 degrees. And so you're basically just cooling diffusively from the cold boundary condition at the top, and you're just cooling into that half space, all right? And you're solving the conduction of heat, so dT, the change in temperature with time, which equals the thermal diffusivity times the change of temperature, basically the curvature of the temperature in space. Okay, and you apply the boundary conditions. The main important one for the half space is that the temperature equals the mantle temperature at infinity. All right, and then you have a surface temperature of 0. And you can solve this analytically with some fun math that's in Turcotte and Schubert's book. And you get this equation for the temperature as a function of depth, y, and as a function of time. Okay? And time, you could basically, age, you can translate into distance from the ridge if you know your spreading rate. Okay? So what this temperature depends on is it depends on the difference between the surface temperature and the mantle. Okay? And this error function, which depends on the square root of the thermal diffusivity and the age, and then how deep you are. Okay? And then you normalize this, you add in the surface temperature at the top. So if you haven't worked with error functions, hold on a second. I've turned this sideways. So this is an error function in red, an error function as a function of x. So x would be everything inside of this, y over 2 square root of kappa t. Okay? And what you can see, if this is basically depth, this looks a lot like what we're used to seeing for a temperature profile, right? So that's, the error function is a very good descriptor of, that's where we get that shape, right? It's from the error function. Yeah?
How does a nonlinear spreading rate affect this?
How does nonlinear
spreading rate, if it weren't just constant? Not constant.
If it wasn't constant,
Variable
right? So you could do a finite difference calculation and have a time varying velocity, but this is an analytic solution with a single velocity, right? But you could put in velocity as a function of time into here and calculate it. Yeah, that's not a problem. But this is just a simple analytic solution. Yeah. Yeah.
Is y here the thickness of the slab or distance?
Y is distance down. So
okay.
Y is depth down. And if you think of age here could also be distance from the ridge. Okay. So here your ridge would basically be up here. Okay. And then you would these are the contours showing the temperature as you go away from the ridge. Okay. So this is 400 degrees, this is 800 degrees, this is 1200 degrees. Okay. As a function of age. Right, for some constant spreading rate. All right. What's important is that at young ages you have a thin lithosphere. Okay, and as you go out, not only is it thicker, but the gradients in the temperature get really spread out. So it cools more slowly as you go off in time. Okay, so if you look at this profile, right, this straight part of this profile is going to cool slower than where you have the curvature here. Okay, this is where you have most of the cooling ends up going on at the bottom of the plate and not inside of it. Okay, so you can use this estimation to basically determine what is the temperature profile of my plate, which is 80 million years old at this trench. That's my initial thermal profile for the plate as it then turns and goes into the subduction zone. Okay, and so that thickness and temperature depends on how old your plate is. Now there's a competing model for this, okay, which I'm not going to go in detail, but it's called the plate model. And the plate model is different because it has a boundary condition at the bottom, which basically says the plate cannot thicken beyond this depth. Okay, so instead of getting thicker and thicker, which is what's predicted by the half-space cooling model, it basically flattens out at about 80 million years old. Okay, and this is based on observations, which are also controversial, that suggest that the surface topography of the plates stops deepening at about 80 million years old, and so the topography basically flattens out. The bathymetry of the oceans flattens out, and that means if it's flattening out, that could be because the slab has gotten the plate has gotten a maximum thickness, and it's no longer sinking isostatically. Okay, so some people will say that actually there's a maximum thickness to your lithosphere as it goes into this to the subduction zone, and that even if you had a plate that was 150 million years old, you'd never really have this temperature of this thick of a plate, right? But I don't want to debate that here. I always use a half-space cooling model. I'm totally happy with it. Doesn't make.
What do you define the plate as?
Well, that's arbitrary. That's why it's a strange model. You base it on observation. But the observations in themselves have a lot of complications.
People to understand what you're saying, the plate thickens. What is plate defined by?
Oh, so the thermal anomaly of the plate thickens. The mechanical part is defined mainly by a colder. This part will be more viscous than the surroundings, but not by very much. And if you have a nonlinear rheology, the mechanical boundary layer will be much narrower. So the mechanical thickness of the plate is maybe actually much thinner and flatter than this thermal halo basically at the bottom. Okay. Yeah?
I want to add something to the plate model because I know Shiji has done a lot of calculation on this, and the conclusion is like if the slab gets too thick, it will cause a small scale instability, and which will seam the slab actually.
Yes. Yeah. So I didn't want to get into all of that here.
Okay.
But yes, so this portion basically that's cold, but just a little bit colder than the surrounding mantle, is actually also shearing, so its viscosity is pretty low. And this will actually go thermally unstable, and you'll start to get lots of small-scale instabilities. It's not clear exactly where the onset is. There's been studies that have been done. The thing is that unlike the plate model, okay, those instabilities basically sink into the uppermost mantle, and they cool off the uppermost mantle, right? So that thermal anomaly is still there. It's just been thinned off and mixed in, whereas here you basically truncate it, and you don't allow that thermal anomaly to exist underneath the plate, okay?
With some additional heat source.
From where?
From below.
Yes. Yes. Yeah. There.
What are the best constraints we have for deciding which of these models is reasonable?
Uh-huh.
We have surface wave models.
Uh-huh.
Garrity's PA5, for example,
Uh-huh.
which gives us a thickness of about 68 kilometers, plus or minus whatever error,
okay,
on 100 million-year-old lithosphere, which is even thinner than what's shown here.
So the question is, what is that measuring, right? So I'm talking about a thermal boundary layer, right? And the shear waves, if you have anisotropic flow, right, in this part, right, and you actually are the question is, what are you actually seeing? Are you seeing a mechanical thickness, right, or are you seeing a thermal anomaly? The thermal anomaly here is, I don't know that would you see that? I actually don't know the answer to the question. Maybe.
I guess I just wanted to comment on this in that it's maybe important to take away that the half-space cooling model has very nice simple physics in it.
Yes.
Which has one controlling parameter, the age.
Yeah.
Right? If you know the geological age, this gives you a prediction.
Yeah.
So it doesn't really depend on the spreading rate. If you know the age of the seafloor, then you have a nice prediction, not just for the thermal structure, but also for the bathymetry. Problem is, some places have both bathymetry, heat flow, and seismological signatures that are consistent with half-space cooling, but at the wrong age, right? Which makes one consistent interpretation that there's been some sort of reheating event. The physics are just like in the first model, but in those anomalous regions, something has reheated. And I think, as Barbara said, having an additional heat source, having internal heating, and having temporary trapping of heat, such as underneath the Pacific, where there's a curtain of slabs around, temporarily impeding the mixing, is one explanation for that. It's important to keep in mind when you have the plate model, it's just saying, well, it just stops cooling for no reason, and let's just clip it, right? So it's a fix rather than a physical model, because there's nothing saying what keeps it constant in there, right?
I guess
yeah.
what I don't understand are the real seismological constraints we have on the thickness, seismic thickness of the oceanic lithosphere.
Okay, so can we hold off until then? Yeah. Okay. All right. So have in the back of your mind a half-space cooling model, okay, or a plate model, whichever you like. But basically, that you have this spreading out of the temperature contours, and so that you have actually the plate, which has a thermal profile that's actually fairly broad, not very sharp, okay, and some of the earliest models for the temperature of the slab, I'm going to run out of time, actually. So some of the earlier models put on boundary conditions that basically fix the top and bottom of the slab to have the same temperature as the surrounding mantle, and completely forgot about the fact that you had an initial thermal structure, okay? That then you have slow rates of cooling and slow rates of heating of the slab from the surroundings. So if you don't take into account this initial thermal structure, and you don't take into account the fact that the slab will cool off the surroundings while it is being heated up, you will get a very narrow slab, all right, with temperatures that heat up very quickly because you have basically a very steep gradient in temperature on the bounds, and so your conduction is very fast. Okay, so taking into account that initial half-space structure is important because the continued heating of the slab from the bottom is very slow. Most of the heating of the slab comes from the top. Okay, so this, sorry, I'm going to move on from that. So in order to get at that part of it, what it really is, the thermal structure, the next step that people have taken is to impose either a corner flow, as they've done here, with either isoviscous or non-Newtonian viscosity. And what happens there is that you have a cold initial thermal structure going in, and then your flow, right, is going to set the thickness of the boundary layer and affect how quickly the slab is going to heat up through that boundary layer. All right, so I'm going to move to the next slide, which has this shown more quickly. So this is a picture from one of Peter Van Kekken's papers. This is a profile for Honshu, I think, in terms of the shape. And so you can see here they has the initial half-space thermal structure, okay, which is important. So when the slab comes under the overriding plate, there's this corner spot where you basically have almost zero temperature. Okay, there is a closed contour in here, so it's more like maybe 100 or 200 degrees. That comes into contact with this very hot mantle wedge. And that is the point that basically starts the heating of the slab as it goes into the upper mantle. And from that point, you start to grow the thermal boundary layer, all right, and the thickness of this boundary layer, which you can see growing here relative to the slab, that is the cooling of the surrounding mantle, right? And as you do that, right, as soon as you start cooling, you actually are decreasing the rate of heating in the slab because anytime you take your temperature gradients, you flatten them out, your rate of diffusion goes down, all right? So what this does is this means that you end up creating sort of this boundary, and you can actually maintain very cold temperatures for the center of the slab, even going down into the upper mantle. So by very cold, I mean temperatures that are 700, 800 degrees colder than the surrounding mantle. Okay, in the transition zone, as you go deeper, it's still 400, 500 degrees. Okay, so the slabs are much colder than what was predicted from very early models that didn't take into account the thermal boundary layers on the sides of the slab. And it was also the problem with those earlier models is that they don't actually have the right mass, right? Because if you're only heating the slab and not cooling the surroundings, you haven't conserved the mass from your slab. Okay?
But it's still the upper half physically of the slab that could be seismogenic, could be cold.
Yeah, so what would be so coming back to the seismogenic part, so it's basically the parts that are mostly in purple. Right? This is what would be seismogenic. And to Brad's question, it may not be the coldest part, because the coldest part may not be easily deformed. It might be sort of the areas surrounding that center point. Okay? And that depends really on the rheology that's active in the slab, and also what the trigger is for the seismicity, which we don't know at the deeper depths. Okay, so I'll skip this last part, and I only have 5 minutes, which was to talk about the phases of subduction. Okay. So I think I'm just going to walk through what they are, and then I want to show one video because I don't have time to go through all of these examples. Okay, so the first phase of subduction is subduction initiation. All right, the key thing to think about in terms of subduction initiation is that, as far as we know, there needs to be some forced compression in order to get subduction initiation to start. There's been lots of attempts to get it to spontaneously start, and it's very hard. Okay, so this is. I'm not going to go into all the details. The next stage is what I call sort of a juvenile slab. This is where you start out with a slab that has a relatively shallow dip. This is probably controlled mainly by the corner flow at this point. But as soon as the slab starts to get a bit bigger, it starts to actually pivot and steepen. Okay? And this is what is predicted by the corner flow, right? That as the slab gets more buoyant and you start to increase it's not being held up by the hydrodynamic stresses anymore. It will steepen, and it will just keep steepening. Okay, and so in these models show that steepening where the slab basically enters the transition zone at almost a vertical angle. Okay, now this slab is not being allowed to move forward or backwards, and if it was, then this could actually have a different shape as it entered the transition zone. The next stage is actually the interaction with the transition zone. I call this the young adult phase because it's, you know, like having a teenager with all the complexity of being a teenager. There's lots of different phase transitions. There's different changes in viscosity. There may be melting going on. There's water. Okay, so it's a complicated phase. What I think is interesting from the observations, okay, is this is from an old compilation of data, but I think this one point can be pulled out of this. This is maximum slab depth, okay, versus sinking velocity. And what you can see is that for slabs that go into the lower mantle, there's sort of a maximum sinking velocity in the upper mantle of about 50 this is millimeters per year, so about 5 centimeters per year. And shorter slabs are basically sort of going up to that level. But only slabs that basically have their maximum slab depth basically right in the transition zone. So these are slabs that look like this, okay? These basically are the ones that can go super fast, right? 3 times faster than sort of the average sinking rate of slabs. And what? These are coming from Lallemand data. So these are plate rates basically broken down into plate sinking velocity. So subducting, this is sinking velocity of a slab, basically taking convergence velocities and taking the dip and turning that into a sinking velocity in the upper mantle. And then this is the maximum slab depth.
From what? From what?
From tomography, seismicity, basically all different types of. So some of these are very short slabs that we don't think go into lower mantle, and then these are ones that appear to be in the transition zone. Some of them are laying flat in the transition zone, okay? But the sinking rate in the upper mantle is very high, all right? And this is what you would expect from basically as the slab first gets into the transition zone. There is a lot of extra buoyancy coming in from the phase transitions, and yet you haven't actually hit the 670 where you have an increase in viscosity. Okay, so the transition zone, the flow, you may get basically an acceleration of flow as the slabs basically enter into the transition zone. And this is one movie that shows this process. This is velocities down here, and you only have to look at the red line, which is the sinking velocity here. And at the very beginning of this, which I'll try to play again. I think I can play it again. Okay, right as it goes into the transition zone, you get the spike in sinking velocity. These are dynamic models, so there's nothing pushing on these. And then as it goes on, you have changes in the rate of sinking as it is interacting with the lower mantle, as it buckles, right? You have basically peaks in sinking rate, and then it goes back up again. I might actually have the wrong. It may be the blue arrow. Sorry, it's the blue one. So it goes up. This is where it enters the transition zone. Here's where it's buckling, and then it buckles again right here. So you have variation in the sinking rate as you are buckling and changing as the slab is allowed to change its orientation and folding in the upper mantle. Barbara?
So this slab is buckling in the wrong direction compared to what we see in seismic tomography?
So this is a completely dynamic slab, and it doesn't want to roll back. Okay, so it could, if it wanted to. You see this back arc that opens up in the top. Okay, it doesn't want to go backwards. My students spent a year trying to get our slabs to go backwards. They don't roll back. So this is probably a problem with the rheology. Okay, and I'm totally willing to admit that. But the folding that may be going on here, whether it's laying back or not, you can still have these variations going forwards and backwards.
Okay? Magali?
Yeah.
What would be the effect of, I'm on the other side. What would be the effect of adding the, like a metastable olivine as you enter the 410, or as you go through the 410?
That would affect the way that this is folding and buckling. It could affect the way it's transmitting stresses up to the surface plate. So yeah, these are not, I'm not saying that these are the solution, okay? These are an example of what happens that we're trying to figure out. And we found that these slabs don't want to go backwards, and I think that's because they have a yield stress and viscosity, and they probably need a Peersall's a low temperature plasticity that will allow them to deform more. These slabs are basically too stiff in this corner. Okay, and that's why I think that in our models, that's why they're not rolling back. Okay, yeah.
Is there any extra flow in the mantle that might be forcing them either way?
Yes, so there could be extra flow in the mantle, right? There could be interaction with other slabs in the upper mantle that's affecting the flow in the upper mantle and creating changes in the pressure conditions around it. The thing that's the one caveat I would say to Barbara's comment that they're folding in the wrong direction. Not all slabs roll back, okay? Some slabs are going to be controlled, right?
Does it have to be rolled back?
I don't know how you can get, so most models that show folding don't show, so let me just show you let me do one thing with this, okay? Hold on. Oh, it went back. It's really, I don't have a thing to drag it. Oh, shoot. So, come on. Hold on, I have to pause it at just the right spot. Okay, there's a section, right, where it folds, and it's folded in the right direction. Okay? So what is the snapshot? What are we seeing in the tomography, in the seismicity? Is it a folding process? Is it one long rollback? Right? So this one's not rolling back. You can get a slab that actually folds and it has a flat tip. It's not super long, but you can get it. Okay? So these are 2D. The rheology may not be right in the corner. I think it might be really important, right? But this shows we're starting to get to some of the complexity, right, that is real in the mantle. And it's super important for what you end up with down here, okay? And these white layers in here are crustal layers, right, that are basically being folded up inside this thermal halo that's going down into the lower mantle. So there's a lot of, we need to do much better models of this to see how you can get long-lived flat regions, how you can get maybe folded sections like this that go deep down into the mantle. We don't yet know the answer to what actually controls all of this, right? Which is great for all of you because it means that there are a lot of questions out there to still answer. Okay, so I will end there. Ending subduction. They die. They break off. I know it's sad. Retirement. This was the life of a. So this is the interaction with the lower mantle. I called the midlife crisis. Folding and buckling. Okay. All right. So I will finish there, and I'll take any more questions. Jenny, Jennifer.
Regarding the last set of cartoons, from some seismic studies, we see that the 410 is not always elevated in subducted regions, and so temperature profiles could certainly vary, as you suggested.
Yep.
And so there could be different forces acting on those systems.
Yep.
And with such a strong temperature gradient, I would expect there to be a large chemical diffusion happening, and that we shouldn't necessarily think of these systems from a mineralogical perspective as these like single entities of morb entering without being, let's say, perturbed, because if there is such a strong temperature gradient, there's bound to be chemical diffusion happening.
So the boundaries are going to get blurred, basically,
Right, and spur off other reactions and perhaps melting, depending on that reaction.
Yeah.
So
that's a great comment. Yes. Yeah. So there's I've thought about that. There's also could be a lot of chemical heterogeneity in the mantle surrounding it, right, which is going to affect what the profiles look like. The other thing I was talking with, we were talking yesterday about the viscosity of the crustal layer versus the Harzbergite layer as you go into the lower mantle, which might be the difference between those two might get really big, right? The morb could be really weak versus the Harzbergite because of the presence of calcium perovskite or not, okay, depending on what that rheology is. So there's a lot of things that are just we don't know, we haven't known, and so we haven't put into the models. But we're starting to get lots of more information from mineralogy in terms of how the whole system evolves. I think taking into effect the diffusion is an interesting question because that will really blur some of this. Yeah.
I think that the time scales for chemical diffusion, especially in the presence of those slab-like temperature gradients, those time scales are probably a lot slower than the time scales for thermal diffusion.
Okay.
And so
even as it goes into the lower mantle?
Yes, diffusion doesn't do anything.
Anything, okay.
Chemically.
By 6 orders of magnitude.
Okay, that's interesting. So diffusion is not going to be important. Okay, good.
What might be the effect of three-dimensional flow in the mantle? Like, for example, toroidal flow, would that tend to flatten the slab or steepen it?
Depends on the width of the slab, what the overriding plate is doing. So I think the three-dimensionality is going to add a lot of complexity into this and a lot of unexpected behavior of the slabs as we keep going. I think in general, some models that have been done so far, the toroidal flow can help to promote rollback in some cases. If for smaller slabs, for larger slabs, it may not be the same. I don't think we know the answer to that question yet. But the three-dimensionality will be important. We saw it in the data of the seismicity for the curiles, right? As you start to get these different slabs basically connected but dipping in different directions, right? You're tearing the slabs, you're going to fold them in different directions, you're going to be able to sort of lay one slab flat while you're tearing in one that's next to it. That's going to have the flow at the tip of the slab as it goes into the lower mantle will be very different than what you see in these simple 2D models. So yeah, three-dimensionality is, we have started to do more of those models now. Juan?
We'll take one last question and then it's coffee break.
Or comment, yeah.
Okay. I was going to comment on that question, but I'll leave that for later. So you talked about the importance of the boundary conditions on the top, but you didn't comment much on the importance of the boundary conditions at the bottom of the model.
Right.
And a lot of people use just a rigid boundary at 660, and that's one of the ways they manage to get folding in the slab
that are always
the
flat.
right way.
Yes.
So what would you say it's worst? Not getting buckling the right way or folding the right way, or using a rigid boundary at the
Well, I think putting
bottom?
a rigid boundary at 660, it controls what your slab does in a lot of ways, right? It really constrains the flow to be an upper mantle flow at a shorter length scale. So when I first started doing these 2D subduction models, I put my bottom boundary at 1,500 kilometers to try to save on computational space. And then I tested it and moved the bottom boundary to the core mantle boundary, and the results were different.
So these results, where is the bottom? At the core mantle boundary?
Yeah, and the model domain is about 60 degrees, right? So it's 60 degrees. Yes. So 60 degrees across, right? Okay. So that's 6,000 kilometers across. Okay. Seems like it should be more than that. Okay. So I tried to push them far away, but I still actually don't think that they're far enough.
Yeah. And one less
I would like to do full Earth models without boundary conditions on the sides.
About the viscosity jump between the upper and lower mantle, which viscosity increase? I mean, if you make a very big viscosity jump, you don't manage to have also folding the right way, right?
If you make the jump bigger, you can get more folding, and the frequency of folding changes. If you decrease it, you get less folding. So we were not actually looking at folding of the slab, so we weren't varying that particular parameter. You can get different length scales of folding if you include the crust and the Harzbergite versus not including it, right? So, or what phase changes you include. So all of those things are going to affect the time-dependent behavior of the slab and how it is shaped as it goes into the lower mantle. Yeah. All right. Thank you, everyone. I'll be around for the next 6 weeks, so ask me questions.
Let's not forget we resume at 11:00.
Geology class. But I'll note that subduction was the last process of plate tectonics that was understood. It was only understood really after the 1964 Alaska earthquake, in which it was demonstrated from the deformation above the subduction zone that you had to have a megathrust going down hundreds of kilometers, okay? And that was when it was understood that you have basically a subducting plate that goes from basically flat lying, right, and slowly curves into the mantle, and that the overriding plate is not participating in that sinking process. Somehow it gets mechanically decoupled from that subducting plate and remains on top, okay? And we see this in this is Honshu, this is Tonga, this is a nice 3D image of the Gorda plate from Richard Allen's website with the Yellowstone hotspot sitting right there. So on our planet, subduction is one-sided, okay? We know when the models that I do, when we do subduction modeling, we basically start the system in such a way that it can only have one-sided subduction. But there are people who work on the larger scale dynamics of trying to create plate tectonics from first principles. And for a long time, all of their subduction zones looked like this, okay, where you have a plate coming in this side, so that the color scale is reversed, so red is cold and blue is hot here. So they would have a plate coming in and a plate coming in, and it would sink, but it would sink like this, okay? That's not what we see on our planet. Okay, and for a long time this was confusing. People thought, is this rheology? Is this something about water? Is it something, you know, what actually creates that asymmetry? All right, and it turned out just a few years ago that there was some insight from some 2D models of subduction that showed that basically the boundary condition on the top of these numerical models, which is what we call free slip boundary condition, crust. And that layer can be very important in terms of the behavior of a plate or a slab because it's also very dry. And we know that dry rocks are usually much stronger than wet rocks. Once the plate makes it across to the subduction zone, we know from our intro geology class that eventually it gets dense enough and it becomes unstable. We don't really know exactly how that happens. And will subduct underneath an overriding plate and eventually come into some shape that looks like this. At the trench, there's usually a little bulge that comes up that is a sort of a flexural bulge of this plate that's called the outer rise. And at that point, you start to get significant faulting of the crust and possibly going into the mantle part of the lithosphere. Okay, that faulting is significant because it tends to draw water into the slab. And that water can be important for the strength of the slab, as well as what happens here in the mantle wedge, the dehydration and melting going into the arc, but also in terms of seismicity in the slab. Dehydration can embrittle or strengthen the slab at depth, and that can be a trigger for seismicity. Okay, and so eventually this is going to go down into the mantle, and what this looks like, its shape, how it deforms, is going to depend on the forces that are acting on that plate. So what we want to do is we want to figure out what observations can we make of subduction zones in order to understand the physical processes that control the physical sort of behavior that controls this process on Earth, okay? Subduction on Earth is very particular, right? And we know from lots of numerical simulations that we can make things that have plates and move around with sort of that looks like mantle convection, but there's some key things that look like our subduction that don't just magically appear in every numerical model we make. So the observations are telling us about what is the key characteristics of the rheology, of the heat flow, of the energy, and how that energy is dissipated in the system that actually defines how subduction looks on our planet. Okay, so what I'm going to do, we're asking this question, which is basically the big inverse question, right, that we're all trying to answer, which is how can we use these observations to learn about the processes that are active in the upper and lower mantle without being able to go there directly. So here's an outline for what I'm going to try to cover. I'll say try because I hope you interrupt me and maybe I don't make it through the whole thing. And so first I'm going to start out with what are the key observations that constrain the dynamics of subduction. These are mainly shallow upper mantle constraints, okay, at this point. How do end-member models inform our understanding of subduction? I'm going to introduce two end-member models that we know both of them are wrong, okay, but they're very, very useful for building your physical intuition about what is important at different stages of subduction. Is it the strength of the slab? Is it the viscosity of the mantle? Is it the density of the slab? What's actually controlling the deformation at different stages, okay? And then I'll explain a couple of simple approximations, mainly for temperature, but I'll also do a sinking calculation for like how long it takes the slab to get to the bottom of the mantle. And then finally, I'm going to walk through what are key processes during different stages of subduction. Okay? Any questions? Okay. All right. So first, I have a repeated slide. That's funny. Okay. First, let's start out with what I think is a fundamental observation about subduction on our planet. Subduction on Earth is one-sided. Okay? Now, this may seem obvious because we've known it since, this is what we see. This is what we're taught in our intro. All right. Hello, everyone. Okay. Hello, everyone. My name is Magali Billen. I'm a professor up at UC Davis, and I am a geodynamicist. I've spent most of my time focusing on various different aspects of subduction, going from the very shallow processes, faulting and fracture at the trench, down into deformation within the transition zone. I haven't actually done any work on what happens to slabs in the deep mantle. Okay, so what I'm going to be doing today is sort of setting up what you might think of as the initial conditions or the boundary conditions for what happens to the slab as it goes into the deep mantle. And so I'm going to start very, very broad and very shallow and be trying to work my way down and give you some idea of the kinds of things that are happening in the upper mantle, which will have a profound effect on what the slab actually looks like when it goes into the lower mantle and how it gets down there. Okay? Please interrupt to ask me questions whenever you'd like. I get really worried if nobody talks back to me. I feel like somehow I've stopped speaking or something. There's no sound coming out of my mouth. Okay, so ask me questions. Okay, so let's just start out with a simple overview of subduction. And subduction is complicated, so making it simple is starting with the basic geometry, I think. So this is a 3D cartoon drawing of the subduction zone. And the first thing is to consider is that the plate that ultimately makes it to the subduction zone is formed at an oceanic spreading center and then has to move across the ocean basin where it thickens and cools and thickens, growing a thick, strong lithosphere in that process. It has a buoyant oceanic crust. And also a buoyant Hartsbrigadic layer, which is the layer that has been melt depleted in order to form that. The free slip boundary condition basically means that you have a wall, okay, and you can't flow up against it, right? The velocities coming up go to zero, and so the flow has to be tangential to that surface. Okay. Now, the Earth does not have a free slip boundary condition on the top. It has a free surface. The surface of the Earth can move up and down. And even though the topography that we see, right, maximum of 20 kilometers or so, is tiny compared to the radius of the Earth, the stresses involved in holding up that topography are significant enough that they can actually create basically the natural conditions, all right, to create an instability so that one side of the subduction will win. Okay, so in this model, what they've done is they've taken off that free slip condition, allowed that little bit of flexure of the plate going into the subduction zone, and now in these global models, you can actually develop one-sided subduction. Now that's important when you're trying to look at the long-term evolution of subduction because this slab looks very different than that slab. This one is thinner. It ends up actually rolling back. Okay. This one is very thick, and it tends to, but they almost always sink vertically with some mantle flow that ends up actually moving them around. Yeah?
I don't believe that at all.
You don't believe it at all? Okay. What was your thought? Because I thought this is pretty significant.
It's a complicated story,
okay.
But I would like to know that there are some, including myself, who think that the free surface is not at all required for one-sided subduction. And the weak crustal layer, sort of by default, does that for you. this particular model setup is very complicated. I had a student trying to reproduce this and trying to